Hello, welcome back to Calculus 2. In this video, I am going to show you, as promised, an example of using WolframAlpha to calculate a Riemann sum. But before we do that, I'd like to introduce some notation that we're going to use and walk you through a couple of easier examples to build up to that. So first, in this definition box at the top, you see the definition of some important terminology and notation for definite integrals. And so by definite integral, I mean kind of what we've been doing in the first couple of videos, which is finding the area under the graph of some function. And so what this notation means is I have some function, f of x, and we're thinking about the graph of that function. And then when you see these little values a and b, the superscripts and the subscripts, that tells me the left and right endpoints of the domain of the function. So I'm thinking of this like that image we saw on an earlier slide here, where I have the graph of some function, and a is the x value on the left, and b is the x value on the right. And so what we're interested in calculating is this area underneath the curve between those two barriers, between the left and the right sides. And that is what this notation represents. That area that I just highlighted back there, that's what this whole set of symbols represents. So I would read this out loud as the integral, that's what that curly S symbol there is, the integral of f of x, of the function f, from x equals a to x equals b. Now, a couple things about this. For one, that symbol you see right there really is, and literally was historically created to represent, an elongated S. It's like a stretched out capital S. And S stands for sum, and it's meant to remind us that this whole thing is based on summing or adding up the areas of a bunch of rectangles. Remember that in the last video where we're looking at approximating the area under a curve by taking little rectangles and adding up, summing all their areas. That's exactly what this S symbol is meant to represent, to evoke that. The other idea is that the word integral or integration itself should hopefully evoke in your mind what we're doing, which is we're taking this region under a curve, we're breaking it up into small pieces, these rectangles, and then we're combining, we're integrating all of those areas together. The phrase definite integral, by the way, is just to distinguish this from another type of thing we'll see fairly soon called an indefinite integral. So think of definite as just saying there's a definite, a specific answer, there's a value. So the result of a definite integral is always going to be some number that represents the area of some region. Some words that you might see and we might use in passing are integrand. That refers to the function that is inside the integral. And meanwhile, the a and the b, they are called the lower limit and the upper limit. So a is on the bottom, lower, b is on the top, it's upper. But they're also sometimes referred to as the left and the right limits because they are the left and right sides of the region. So just be aware that we refer to those as the upper and lower limits of the integral. One other thing that I realized I didn't put on this slide, but I probably should have, is that there's this little dx symbol in the integral there. Now, that represents a couple things, and it's maybe hard to appreciate for now because the things I'm about to say are based on, well, later, but try to take my word for it, that later on, perhaps in a Calculus 3 course, you will have some functions that have not just one input, x, but multiple inputs, x, y, z, any number of variables. And so that little dx there is a reminder that we're using the variable x as the one that's changing, that's varying left to right. And so when I see those limits a and b over there, the dx is a reminder that we're integrating with respect to that particular variable. So it's from x equals a to x equals b and not some other variable. Again, that may seem like, unnecessary for now because we only have one variable in this function. It's f of x, right? But in the future, you will certainly see some examples with multiple variables. So here are a couple of examples. These are the earlier examples we did, let me jump back to those. Remember the first one we did with a constant height, the function was 4, and we integrated over the first 6 seconds, and we found the total area to be 24. That is exactly what this says in integral notation. Take the function f of x, and there I can see it's just the function 4. And then, oh look, there's that dx to remind me that that's where the function ends, where the integral ends. And then I can also see that we're going from x equals 0 over to x equals 6, and we found the area to be 24, and that's the definite integral output, 24. These other two definite integral statements over here come from example 2 that we were looking at. So in that one, we found that from 0 to 4 of this function, where f of x was 4 minus x, or back then I wrote it v for velocity and t for time, it's 4 minus t. When we went from 0 to 4, the result was an area of 8. And then when we went from 4 to 6, the area was underneath, so it was negative. And so collectively, if I thought about the whole thing from 0 to 6, we found a displacement of 6 feet. That's precisely what these things are saying. When I go just from time 0 to 4, I ended up with an output of 8. And when I went from 0 all the way over to 6, I ended up with an output of 6 total. But notice it's the same function inside. All right, I would like to give you a chance to try a couple of these problems. I'm going to put this on the screen here so you can pause. And the next slide has all of the solutions to these practice problems. So I would recommend pausing the video here, and then I will skip ahead to the solution slide, and then you can pause it there to check out your answers. And then after that, I'm going to move on and show you another example. Okay, here are the solutions to those practice problems. I'm hoping that you're able to create the function formula for these examples based on the wordy description of how the marble is changing its velocity over time. And then from those function formulas, I hope you're able to draw or sketch the graph, or maybe vice versa. Maybe you draw the picture first and then you think about what the function formula would be, however you want to do it. But you can use what's on the screen here to check your answers. All right, here's what's next. I'm going to make a recommendation, because sometimes we get lucky and an integral looks really challenging, but actually represents a nice simple shape that we already have an area formula for. So pause here and take a little bit of time to think about what this integral means. Look at this notation and try to refresh your memory of what this represents. Here's the function, and here are the upper and lower limits. What's the output going to be? What's the definite integral value of this? Think about what the graph of that function looks like on that domain from 0 to 4. All right, ready to check the answer? Let's delete that box and see what it is. And you'll realize it's part of a circle. The graph of that, function is the top half of a circle. This is square root of 16 minus x squared. It's the top half of a circle with radius 4 centered at the origin. What you see right here is a little bit of algebra to try to convince you of that. The upper and lower limits of 0 to 4 tell us that we're starting at x equals 0 and ending over here at x equals 4. And so this integral is really asking us for this shaded region right there. What is that area? And I hope now that you can see that that's just a quarter of a circle. And so there, pi r squared, that's the area of the entire circle. And I have just a quarter of that, just the top right quadrant. And so I end up with an answer of 4 pi. Now, a little bit later in the course, we're going to actually learn some algebra techniques to see how to solve this problem in a slightly different way, but I hope you see that right now, this is pretty much the easiest way to do this. So that's my title here. Look out for regions that are nice, simple shapes that we already have area formulas for. However, at the same time, I have to make the recommendation that we need to be on the lookout for areas that are not nice, simple shapes. So for example, I picked this one because the setup and the function look almost identical. I just got rid of the square root. Let's do 0 to 4 and 16 minus x squared instead of square root of 16 minus x squared. But it turns out that changes a whole lot. It's similar in the sense that I have this region like this, and I'm asking for this total area, but don't be misled. I actually changed the scale. Notice how the x-axis goes from 0 to 4, but the y-axis goes from 0 up to 16. So if I were to do this in a scale that was kind of equal in both directions, it would look a lot more like this. It would be a very tall region like this. So this really isn't a quarter of a circle at all, like the last example. It's not part of a circle in any way, shape, or form. It's a parabola. It's something different. So how do I find this area? Well, let's use this rectangle idea. Let's set up an expression that's going to find the area of some approximating rectangles. And then maybe we can hunt for some patterns and set up some technology to do some number crunching for us and explore the pattern to get a particular answer. So I have written here, let's estimate the area using 4 rectangles with left-hand endpoints. Let me try to draw that up here. I'm going from x equals 0 to x equals 4 as the upper and lower limits. So when I cut it into 4 pieces, that's going to be 1, 2, 3, and 4. And when I say left-hand endpoints, that means I'm going to look at the left-hand side to decide how tall a rectangle is. So for the first rectangle from 0 to 1, I'm going to base the height on how tall the function is at the left-hand side, which is where x is 0. And that's going to be at a height of 16. And why is that? Well, when f is 16 minus x squared, f of 0 is 16 minus 0 squared, it's just 16. That's why that height right there is 16. And then f of 1 is going to be 16 minus 1 squared, it's going to be 15. And that's going to be the height here of the second rectangle. And then at x equals 2, the height up there is going to tell me how tall the second that rectangle is, the third one, and so on. And that's what's going on in this expression down here. What are all of those ones? Let me highlight those in red. Those single ones right there, that is the width of each rectangle. I know it's kind of redundant to write times 1, but I'm doing that to remind you that that's the width. When we have the area of a rectangle, it's always width times height. And in this case, all of the widths are just 1. And meanwhile, the heights are coming from the values of the function at various x values. So this is the height of the first one. That's the height of the second one, the height of the third one, and the height of the fourth one. Now in the line below that I have all the numbers crunched, and just to give you an answer to look at. I get a total of 50. But I'm much more interested in looking at the pattern in the red and the blue highlights there. What's the pattern there? What is the red number 1? Where is that really coming from? Well, it's because I had 0 to 4. So that's a total width of 4. And I'm using n equals 4 rectangles. And so 4 divided by 4 is 1. That's why all of the widths of the rectangles are 1. That's really where that came from. And meanwhile, what's the pattern in the blue highlights, the heights of the rectangles? Well, they're all f of something. They're all me plugging in certain x values into the function of 16 minus x squared. And I'm plugging in 0 and 1 and 2 and 3. And where did those come from? Well, it's the starting value on the far left of 0 plus 1 each time. And why 1? Because that's the width of each rectangle. So I'm adding 1, and then I'm plugging in another 1, and then I'm plugging in 1 more. I'm increasing the x value by that little width amount each time. So here's that pattern. This is what I was just showing you in red on the last screen. 4 minus 0, that's the total width of the region. And I'm dividing by n, which remember in our first example on the last slide was just n equals 4. But I could do this for any n. So I'm trying to, on this page, generalize to an arbitrary value of n, for a generic one, not just for n equals 4, like we drew on the last page. So here, this 4 over n is the width of each rectangle. Just like the 1 on this page here. Meanwhile, how about the height of each rectangle? Remember that came from plugging into the function a specific x value. Well, let's think about what the first rectangle was. Since we're doing this on the left and we start at x equals 0, the first thing I'm going to plug in is x equals 0. What's the second value I'm going to plug in? Well, in my example back here, I plugged in x equals 1, because that was the next x value. But over here, when I'm thinking about a generic value of n, this little width of each rectangle tells me what the next x value is going to be. It's going to be just one of those. And so here I am plugging in x equals 4 over n into my function. And so there's that value right here. That's f of 4 over n. What's the x value of the next rectangle height going to be? Well, back here it was x equals 2, because I've taken 2 jumps over. I'm going into the third rectangle, the next one, and so I've jumped over twice from the starting value of 0. And so same idea here. I go from 0, make 1 jump to 4 over n, and I make another jump to twice that much, 2 times 4 over n. So I'm going to plug that in for x. And so on and so on. I just keep doing that. I'm going to increase the x value by that little amount, 4 over n, each time. And when am I going to stop? Well, I want to have n rectangles total. So back here I ended up stopping at x equals 3, because that was 3 jumps, 1, 2, 3. And 3 was 1 less than n. My n was 4 over there, so that's why I have an n minus 1 here for the ending point. I'm going to make that many jumps over to the right. And then what we're going to do is combine all of this information to write down the area of each rectangle and add them together. Remember that the red thing up here, that's the width of each one. And all of these blue highlights in the boxes are the heights of the rectangles. And so the area of each rectangle is width times height. So let's just do all that. Let's take the width of a rectangle here times the height of a rectangle. That's what's in blue. And then by adding them all together, by summing them, I will find the total area of all of those rectangles. So again, the red highlight there is the width of every rectangle. The blue highlight is the height of each one. And the green is the notation that tells me I'm summing all of that stuff together. Now, this is the kind of thing that we could spend some time learning some algebraic symbolic manipulation techniques, but I don't think we'll benefit a whole lot from doing that. And so I will recommend that we just use WolframAlpha to do that. So that notation, the K, represents which rectangle we're talking about. And this sigma, the summation notation, says start at k equals 0, the very far rectangle to the left, and increase k up to 1, to 2, to 3, all the way up to n minus 1. That's going to be the last rectangle, the furthest to the right. And you can see the one place that k appears in the formula there is here to tell me how many jumps over to the right I am to find out which rectangle I'm in. Just like over here, I had, well, the first rectangle, I didn't have any. I made 0 jumps to the right. And then in the next one, it was 1 jump, and then it was 2 jumps, and then all the way until the very end, it was n minus 1 jumps. Just like back here, I had when k is 0, I'm talking about this rectangle, and then when k is 1, I'm on this one, and k is 2, and then k was 3 at the end. That's what this notation represents. And now let me show you where this result comes from. Here I've opened up WolframAlpha, and I'm just going to paste this in. I typed this earlier, but this is what you could type. A sum, just to tell it I'm doing a summation of some kind. And then I've just typed the formula, the expression that's in the summation. So let me jump back to show you that. I have the width of 4 over n times, and then in big parentheses, this expression, 16 minus k times 4 over n all squared. And so if you see over here, I've just been careful with my brackets and parentheses to say those big brackets. And you can see how they're highlighted in green right there, which is kind of nice. It's highlighting all of that stuff inside is 16 minus, and then again, there's k times 4 over n highlighted in green all inside those parentheses. That part is all squared. And then to indicate the summation limits from 0 to n minus 1, I can just type in words from k equals 0 to k equals n minus 1. And that's it. It will recognize that that's what I'm doing. I don't have to type the symbols necessarily. You can kind of use some words like that. I'll just hit the calculate button. It does the work for me, and it comes up with this expression. And that expression you see on the right there, the 32 times that stuff over the 3n squared, that is exactly what I have on the slide here. That's the result. And then one last thing to do here, let me open up a new page to show you that, is I had 32 times, let me make sure I get this right, 4n squared plus 3n minus 1 all over 3n squared. This is the area, remember this is approximated, of the actual area from using n, a generic number of rectangles. And so the idea here is that the actual area that we want, the actual area under the curve, is going to be equal to the limit as n approaches infinity of that expression. What we found in that big blue box is the approximate area from slicing the region into some number of rectangles, a generic number n. And if you can imagine taking more and more and more rectangles, remember when we looked at that back here? And it looked like the region was being approximated better and better as I took more rectangles? That's what this limit accomplishes. If I take that expression and take a limit as n goes to infinity, it will give me the correct value of the actual area. So let's put our calculus limit hats on and think about how to find the limit of an expression like this. So I'm gonna distribute that 32 in everywhere. How about that? 32 times 4 is 128 n squared. 3 times 32 is 96. And if you think about it, as n increases, as n goes to infinity, the n squared terms here will dominate, and the 96n and the minus 32, they will be dominated by the large n squared that's growing much faster. And so in the long run, in the limit, I will end up with just the ratio of these coefficients of 128 and 3. And hey, look at that. 128 over 3. That's the actual, honest to God, correct area, the correct value of that integral. It's the area under that parabola. Now here, just to tie everything all together at the very end here, let me just show you how to graph that on Desmos and calculate that as well. Let's make a function. I'll call it f of x, and I'm going to call it 16 minus x squared. Let me change my view along the x-axis here, because I only want to zoom in from 0 to 4. And then I really want to graph just what's the area under that function. Whoops, sorry, I forgot a y there. I want to graph all the y values between 0 and f of x. And then I specifically only want to do that from 0 to 4 along x. There we go. And so now you can see there's that blue region. That's what we're calculating the area of. And let me show you that you can actually do this on Desmos. If I type INT, oops, sorry, I have my caps lock on. If I type INT, notice how that turned it right into the integral sign. Watch that again. Look on the left. If I type IN, when I hit the T, it knows that I mean integral, and it puts the integral sign. And it gives me little spots on the bottom and the top to type the limits. 0, I'll put my cursor in there, and I'll type 4. And then over here, I just need to put parentheses, the function that I want, f of x. And I can use f here because I've called this f in the very top line. If I had called this something else, like y equals whatever, then it wouldn't know what I mean down here. But now it does, because I called it f in the first line, so when I type f in the third line, it knows I mean that function. And look, you see the little caution triangle with the exclamation point in it? It's giving me an error of some kind. Let me tap on that to see what it is. Integrand, hey, remember that word? The stuff inside the integral? Integrand must end with an integration variable like d of x. Oh yeah, remember when I said that d of x was important? And it's a reminder of what variable we're using? Hey, Desmos cares about that too. So that's telling me in here, in the parentheses, I just have to type a dx at the end. Oh, oops, sorry, I'll put it outside the parentheses. And hey, look at that, 42.6. I wonder what that number is. Do you see the little circle with the fraction inside it to the left? If I tap that, it's going to convert that decimal into a rational number, a fraction. And lo and behold, 128/3, exactly what we found over here. Next time, we'll talk about perhaps a better way to do this that involves some algebraic manipulation of the function itself. But for now, I hope that this gives you a flavor for what Riemann sums do. They take the area under some curve, they approximate it by chopping it up into a bunch of rectangles and adding together all the areas of those rectangles. We can use some technology to find an algebraic expression for that sum, and then we can take a limit, which is what would happen as we did more and more and more approximating rectangles and get a better and better and better estimate for the area. And then that will give us the exact area that we're looking for. All right, I'll see you next time.